when this satellite is orbiting around the Earth uh, in an orbit of radius r, then it has total mechanical energy, which is half m v naught squared minus gmm by small r, where v naught is root gm by small r, right? That's the orbital speed. That's the orbital speed. So this would turn out to be half gmm by small r minus gmm by r, so which is minus half gmm by r, right? That's the total mechanical energy in an orbit of radius r, kinetic and potential. So now the satellite which is losing energy, eventually falls on the Earth because of frictional forces acting. It loses its mechanical energy and eventually descends on the Earth. So when it's at radius r, this is its energy, initial energy, and its final energy is minus half gmm by the radius of the Earth. When it descends on the Earth, then this is its final energy. Small r becomes Re. The total energy that is lost is Ei minus Ef, is the energy lost. And it's lost at the rate of c joules per second. So if it takes t seconds, then c into t is the total energy lost. So then from this you can compute the value of t, Ei minus Ef by t. That's going to give you the value of t, the time it takes to fall onto the Earth. So that was problem 1, just to be on record. A solid sphere of mass m and radius r, problem 2. A solid sphere, mass m, radius r is placed at a distance of 5r from the center, from a point mass m as shown. Due to a shift in position at a distance 3r from the point mass, now the point mass distance 3r from the point mass, its radius, its mass obviously will remain the same. Mass is small m. Radius increases to 2r. Find the work done in the presets. Hey, what's the total energy here? What's the total energy of the system? 1, there is interaction energy. E1. There is interaction energy, which is G mm by 5r. That's the interaction energy. Plus, there is self energy of this. There is self energy. If you recall, if you recall, there was a solid cloud of charge of radius r, and if q was the total charge in it, then 3/5 kq squared by r was the self energy of such a distribution. So in this case, instead of k you have g, instead of the plus sign you will have the minus sign, and instead of the charge you will have the mass. So the self energy of this is going to be minus 3/5 g small m squared by the radius r. That's the self energy. Minus, realize that there is a minus. Wherever you see a plus in electrostats, you will see a minus here in gravitation. And 3/5, instead of k you have g, instead of q you have m. Minus 3/5 gm squared by r, that's the self energy, interaction energy. So this is the total potential energy initially, right? What's the total potential energy? Finally, again, there is interaction energy, which is minus gmm by 3r minus 3/5 gm squared by 2r. The work done would be work done is going to be change of potential energy, final potential energy minus initial potential energy. I'm talking of the work done by an external agent, say. But if I talk of the work done by the forces, gravitational forces, the forces of the field, then that's going to be EI minus EF, right? But if you look upon it as work done by an external agent, that's going to be change of potential energy, final minus initial. So work done by an external agent is going to be EF minus EI, and the work done by the field is going to be minus of EF minus EI. We are assuming that no kinetic energy is added to the system. If kinetic energy was added to the system, then the work done by the external agent would be this plus change in kinetic energy. Got me? Yep. Problem 3. There are two particles of masses m1 and m2 very far away from each other and at rest. Eventually, under mutual forces of attraction, they approach each other and they arrive at a distance d from each other. And at such an instant, let's say their velocities are v1 and v2. So their relative velocity would be v1 plus v2, and I want to find the relative velocity at this distance. Now, first of all, I'll solve the problem from a fundamental premise, but that's not recommended. That's not what I want you to do for the problem, but for the heck of understanding what's happening, I want you to be able to solve this problem from first principles, right? So in first principles, the total mechanical energy will remain preserved. The total mechanical energy here is 0 because kinetic is 0, very far away from each other, so potential energy is also 0. Now when they are at a distance d from each other, the total potential energy is minus g m1 m2 by d, and then there is kinetic energy half m1 v1 squared plus half m2 v2 squared, right? But as they move under mutual forces of interaction, that is in the absence of external forces, they also preserve their total linear momentum. Total linear momentum to begin with is 0 and will remain 0 at all times, and therefore m1 v1 minus m2 v2 must be 0. So m1 v1 must be equal to m2 v2. From these two considerations, you can solve for v1 and v2, and therefore find v1 plus v2 the relative velocity when they are g apart. Alright, but this is not what I want you to do. It's a lot simpler problem than this. It should be handled in one shot, in one line. Because this involves writing this equation, solving for v1 and v2 and adding v1 and v2, right? This is not what should be done. If you are only seeking the relative velocity, those of you who've been attending my classes lately in class 11 would realize that if there is a pair of masses, then in the center of mass frame, their kinetic energy is going to be half mu into v rel squared. V rel is what I'm seeking, so why not hit directly, right? So half mu into v rel squared, where mu is the reduced mass, right? So now the total energy here is half mu into v rel squared. So I'm writing the energy equation in the center of mass frame. In the center of mass frame, half mu into v rel squared is the kinetic energy in the center of mass frame, and then there is potential energy, which is minus g m1 m2 by d, right? And when you started with v rel was 0 and d was very large, so the total energy in the center of mass frame was 0, and this gives you direct access to v rel. V rel mu you can write as m1 m2 by m1 plus m2 and obtain v rel from these considerations, right? Clear? 4. Earth, mass m and radius r, and there is a through and through tunnel dug through along the diameter. And T1 is the time it takes to go from the surface of the earth to the center, from A to O. Alright. T1 is from A to O. Obviously, the force between the earth and the particle varies as the particle goes from A to O. It does not remain constant. It does not remain constant. In fact, at some instant of time when the particle is at a distance r from the center of the earth, let's say the particle of mass small m is at a distance r from the center of the earth, the force that it experiences towards O is not going to be because of this annular shell. It's only going to be because of the sphere of radius small r. That's the force that it experiences. Yes or no? Right? I mean, that's a direct consequence of Gauss's law, so to say. Right? It's going to experience a force because of this inner sphere, not because of the shell, not because of the shell. So now, the force that it experiences is G times, when it's at this point, the force that it experiences towards O is G times the mass of this shell. Well, m by r cube for the bigger sphere into small r cube. That's going to be the mass of this. Mass is proportional to the cube of the radius into divided by r squared. G times mass of the earth into mass of the particle divided by r squared. That's the force of attraction between the earth and this particle. And realize that Gm by capital R squared is G on the surface of the earth. Is G on the surface of the earth. So Gm could be written as G on the surface into R squared. G on the surface into R squared. So G by R, mg by R into small r. That's the force that it experiences towards the center of the earth, which is proportional to the distance from the center of the earth. The motion of small m therefore is simple harmonic, with the force constant being mg by r, So k is this. So the omega of the motion is going to be root k by m. So the omega is root g by r, the omega of the simple harmonic oscillator, and the time period is going to be 2 pi by omega, 2 pi to root r by g. And the time it takes to go from A to the mean position is a quarter of a time period. It's quarter of a time period, so T1 must be T by 4, 1/4 the time period, so which is like a pi by 2 root r by g. And T2 is computed on the premise as if G remains constant across AO. If I imagine G to be constant between A and O, then the time taken is T2, right? So that's only figment of our imagination, that's not true, but T2 can be computed from, let's say, from A to O, it travels R at a constant G and takes T2 seconds, right? So T2 then becomes root 2R by and this gives you an opportunity to compute T1 by T2. T1 by T2 could be a state of the. Have you attempted more than this? You have. So this result you might also want to remember. You dig a tunnel through and through, and a particle is released at one end of a diameter. It's going to execute simple harmonic motion across this diameter, with these being the extremities, this being the mean position, with omega equal to root g by r or time period equal to pi by omega. This result you might want to remember. It could be used as a ready reckoner for an examination. Time period of oscillation across a tunnel dug through and through along a diameter is going to be 2 pi root r by g. It's worth a recall. Okay? A man can jump over b equal to 4 meters wide bench on earth. And 4 meters is very small for any variation in g to be accommodated, right? So he launches with a velocity u, and for a maximum range he would have to launch at 45 degrees, right? And he can launch up to 4 meters, right? Very clearly then, 4 is u squared sine 2 theta by g. So u squared by g is 4, where g is g on the earth, on the surface of the earth, g on the surface of the earth. So u squared is 4 times g on the surface of the earth, right? Now, when he goes from the earth to some other planet, g changes, but his capability of u does not change, because that depends on the strength he packs in his arm. So he can give the same u. But now he wants to give a u in a manner that it's able to escape from the planet. The particle is able to escape from the other planet. That means the u that he is able to give must be greater than or equal to root 2 gr for the planet, root 2 gr for the planet, for it to be able to escape the gravitational field of that planet, right? So this u square has to be greater than or equal to 2 times g of the planet into r of the planet. Such is the requirement, right? So which means this gives me 2 times g on the earth. G on the earth is, that is on the surface of the earth. This also is g on the surface of the planet, right? G times the mass of the earth divided by r of the earth squared, right? 2 times greater than or equal to g on the surface of the planet is g times the mass of the planet divided by rp square into rp, right? Now, it's also given that the mean density of the planet is twice as much as the mean density of Earth. That's given, right? Capital G gets cancelled. Mass of the Earth proportional to the density of the Earth and proportional to the cube of the radius of the Earth, right? So r cubed by r squared would give me re, yes or no? Greater than or equal to mass of the planet proportional to the density of the planet into, in any case, mass of the planet proportional to density of the planet, which is 2 rho, into cube of the radius of the planet. So rp cube by rp squared would give me rp into rp, which is rp squared. Fair enough? So that evidently gives me rp squared is less than or equal to re. That means the maximum rp is root re. The maximum rp is root re. So if the radius of the planet does not exceed the square root of the radius of the earth, then he can launch a particle to escape the gravitational field of the planet, right? That is the requirement. And radius of the earth is 6,400 kilometers. 6,400 kilometers. Not that you have to remember the radii, etc. And in a typical exam, no one would expect you to remember the radius. So that was problem 5. Just for convenience, I draw it like this. It does not matter really. There's a particle of mass small m at the center of the semicircular wire. And this wire has mass m and radius r. So it has mass per unit length m by pi r for the ring. Mass per unit length of the ring is m by pi r, right? And I want to find the force of attraction between the ring and the particle. Now, what I do is, I start by selecting various segments of the wire. I select a point particle on the wire located at theta and spanned over d theta. So this length is like a rd theta. What's the mass of this? The mass of this is going to be lambda into rd theta, right? So the mass small m is here, and this is the point mass located at theta, then it will experience a force Gf towards the center. It will experience a attractive force Gf in this direction. This mass m will experience a Gf towards this element in this direction, and this Gf is going to be given by G times the mass of this, which is lambda into r d theta. Lambda is m by pi r into r d theta into the mass of this gmm divided by r square. That's the df, but realize that the various df's are in various directions. So you can't integrate df to get the total force. These are df vectors in different directions. So the net force is not the algebraic sum of these df's. What you might want to do is, you would have to resolve the df as, let's say, df sine theta vertically and df cos theta. And if you exploit symmetry, there is a symmetric element located at this theta and will experience a similar df, and the df cos thetas will cancel off in pairs. The df cos thetas will cancel off in pairs and the df sin thetas will add up. So what we want to do is add up all the df sin thetas, add up all the df sin thetas. So the net force in the vertical direction accommodating this element plus this element is going to be 2 df sin theta. Right? You want to sum it up where theta runs from 0 to pi by 2, because I have included the effect of all these elements already by saying 2 df sin theta. If I had only said df sin theta, then I would integrate from 0 to pi. But since I have said 2 df sin theta, that means I have included the effect of elements greater than pi by 2. You know what I am saying? If I integrate df sin theta, then I would say 0 to pi. But if I said integrate 2 df sin theta, that means the effect of this element as well as this element is incorporated. So I just have to cover a quarter of the circle to include all elements. If I say this 2, if I didn't have that 2, then integral df sin theta, theta runs from 0 to pi. But this 2 takes into account elements on the left of this vertical direction, right? So 2 df sin theta, theta is going to be from 0 to pi by 2. If it was not 2, it would have been 0 to pi. So that's the force, let's say, in the y direction. Net force in this direction, attractive 2 times Gf, as you can see, is Gmm by r squared pi r squared sin theta d theta. Theta runs from 0 to pi by 2. Obviously, integral sin theta 0 to pi by 2 is going to be, everything else comes out. So 2 gmm by pi r squared, 2 gmm by pi r squared, and integral sin theta d theta 0 to pi by 2 is going to be 1 anyway. Right? So that's as far as the force is concerned. Now you would have obviously connected it to what, connected it to the practices that you had adopted in electrostats. If there was a uniform charge of wire and there was a point charge here, then to find the force between the ring, the wire and the charge, this is what you did. You broke this up into elemental charges, dq's, located the charges by theta and summed up the effect of all the charges by causing theta to run from 0 to pi by 2 or 0 to pi as the case is. Right? This is what you did. Got it? Now, the potential at the center of the ring. So this is the force of attraction between the particle and the wire. The potential at this point, that means the interaction energy between this element and this mass. This element and this point particle is going to be G times small m into the mass of this, which is m by pi r into r d theta, right? This is gmm divided by r with a minus sign, GMM by R with a minus sign, right? That's the potential energy of this pair. So the total potential energy, that is the total interaction energy of the system, is going to be, when you sum it up, now you don't have to resolve because this is a scalar, right? Theta runs from 0 to 5. So that obviously will give you minus GMM by pi R. GMM by R. GMM by R. Pi will get cancelled. That's the total potential energy. Now the work required by an external agent to displace the particle from the center of curvature to infinity. At the center of curvature, that is at O, so the potential energy of the system, at infinity, 0. So the work required by an external agent is going to be U infinity minus U0. U infinity minus U0 is going to be the work done by an external agent. Right? Assuming no kinetic energy is added. Kinetic energy is added, then the work done by the external agent would be this plus half mv. Right? A person brings a mass of 1 kg from infinity to A. Initially the mass was at rest and it moves at a speed of 2 meters per second at a speed A. The work done by the person on the mass is minus 3 joules. Problem 7. The work done minus 3 joules by the person, that must be change in potential energy plus change in kinetic energy. Change in potential energy is m into UA minus U infinity. That's the change in, where U is the potential at A. U is the potential at A, joules per kilogram, right? Plus half mv squared minus 0. That's the change in kinetic energy. Clear? So this makes it, m is given to be 1 kg. U at A is what we want to obtain. And then this is half 1 into v squared, which is, so UA then turns out to be minus 5 joules per kilogram. 5 joules per kilogram. That's the potential energy of a unit mass when placed at. Got me? Problem 8. There is a uniform spherical shell. V and E be the potential field, gravitational potential and gravitational field at a distance r from the center of a uniform spherical shell. Realize that if you look at this surface, just to the left of the surface, E is 0. Right? Yes or no? Same as that of electrocharged shell. The charge you have mass, inside the shell, E would be 0, V would be constant, V would be constant, right? And just outside, it's going to have E equal to minus GMM by, or GM by R square. Just outside, it's going to have E equal to, let's say, GM by, E equal to GM by R square. Yes or no? So do you realize when you go from the immediate left of the surface to the immediate right of the surface, E abruptly changes from 0 to Gm by R square. E abruptly changes from 0 to Gm by R square. So E is discontinuous on the surface? E is discontinuous on the surface? Yes or no? Because there is an abrupt change from 0 to a non-zero value across the surface. Right? V, however, is not abrupt. V on the surface is minus GMM by R, and that's the V inside also. So V is continuous, but E is discontinuous. V is continuous, but E is discontinuous. I mean, even if you find one point of discontinuity, it would be looked upon as discontinuous. So this is the surface of discontinuity for E, but not that for E is continuous, E is. You have attempted more than this? No? No? Then I want to give you time. Just one thing. Suppose the gravitational field varies inversely as the nth power of the distance. Don't say as the nth power, just modify this. Suppose the gravitational force varies inversely as the nth power of the distance. Inversely as the nth power of the distance. Then the time period t of the satellite, etc. is right. Please work on this. So now problem 9. So there is a circular orbit of time period t, and the force varies as the inverse of the nth power of the radius r. Right? So then, what does this force provide? The required centripetal force. Centripetal force. So the centripetal force would be m omega squared. Omega is like 2 pi by t. Omega squared into the radius r. That's provided by k by r to power. Right? So evidently, t squared, as you can see, will be proportional to r to power n plus 1. So t would be proportional to r to power n plus 1 by t would be proportional to r to power n plus 1 by 2. Right? Simple. Now for the next problem, problem 10. There is a spherical mass m of radius r, from which you excavate a sphere of radius r by 2. So now if this whole thing is of mass m, then the mass of this would be m by 8, because mass would be proportional to the cube of the radius. So the mass of this is going to be m by, right? Now the gravitational acceleration at this point p, if this was not excavated, the gravitational potential, the acceleration at the point p, that is g at the point p, would have been g times m divided by r squared, would have been the g at this point, right? But now remove the effect of this. The effect of this is like g times the mass of this, which is m by 8, divided by r by 2 squared. So that would be the net g at p if this excavation is carried out. Now, problem 11. From the point P, a mass small m is carried to a height h very slowly by an external agent. Very slowly. That means there is no change of kinetic energy, right? Now, if h is much smaller compared to the radius, then g is practically constant. And the external force applies an upward force, external agent applies an upward force equal to mg all the time, which is a constant force. Then the work done by an external agent would have been how much? Mg into h. Not minus mgh, but mg into h must have been the work done by an external agent, because the displacement is upwards. The external agent applies an upward force mg to counter the weight downwards to avoid acceleration. Right? So mg into h. In the event, h is much smaller compared to r. Now, if h is comparable to r, h is r, or let's say some significant multiple of r, then you can't imagine g to remain constant. G is then going to vary. Right? So now, if h comparable to r, the radius r, then g does not remain constant. Then to carry the particle from P to Q, well, at Q, what's the potential energy? Minus gmm divided by, let's say, small r, right? The potential at P is minus gmm. The potential energy at P is gmm by the radius of the earth, right? Where G into M could be written as G R squared. Could be written as G R squared, G on the surface of the earth. G on the surface of the earth. The work done by the external agent obviously is going to be UQ minus UP. UQ minus UP would be the work done by the external agent, where wherever required you could write GM as G on the surface of the earth into square of the radius of the earth. Right? Now, if H is equal to R, then this case is valid. If H is equal to R, then this case is valid. If H is equal to R, that means if this small r is 2R, if this small r is 2R, then very clearly the UQ minus UP is going to be GMM divided by 2R. This minus this, UQ minus UP is going to be GMM by 2R, yes or no, if H is equal to R, right? But GM you can write as G on the surface into square of the radius of the earth. So then this would become half mgr. If H is equal to R, the work done by the external agent is going to be half mgr and not mg into R. Mg into R would have been if G was constant. G is varying. And if H is comparable to R and if H is equal to R, then the work done by the external agent is half mg into. So C is true, not D, not D. B and D could have been readily eliminated because the work done by the external agent is only positive. Upward force, displacement upward. So it couldn't have been negative, right? MGH for all H is plus 10. Doesn't make sense. So even by elimination, C would have been the right option without doing all this, right? Because all other options are absurd, right? A satellite revolves around the Earth in a circular orbit of radius r. The Earth the satellite, let me call it R1. In an orbit of radius R1 with a velocity V0. So obviously V0, the orbital speed, is root Gm divided by R1. Gm divided by R1 is the orbital speed. Now, a particle is projected from the satellite in the forward direction with relative velocity equal to this much. So from this point P, a particle is projected with V relative equal to root 5 by 4 minus 1 into V0. Root 5 by 4. This is the relative velocity of the particle that is being projected. That means the absolute velocity of this particle would be Vrel plus V0. This is relative to this particle. So the absolute velocity of this particle would be relative velocity plus the velocity of the observer, which is V0. So if you add these two, then the particle from P at a distance R1 is projected with an absolute velocity, call it V1, equal to root 5 by 4 to V0, where V0 is root Gm by R1. Yes or no? Clear? Now do you realize that this is less than root 2 but greater than the orbital speed? This is greater than the orbital speed but less than root 2 times the orbital speed. So whenever that happens, the path assumed is going to be an ellipse. If the velocity of launch is greater than the orbital speed but less than root 2 times the orbital speed. See, if it becomes equal to root 2 times the orbital speed, it would escape the gravitational field, right? So if it's, which it is, right, it's less than root 2 times the orbital speed at this point. Therefore, the trajectory pursued is going to be an ellipse, right? Now, so eventually I want to find the farthest it goes from the Earth. The farthest it goes from the Earth. The trajectory. This is the farthest point, F. At this point, say V is the velocity and R is the distance from the Earth. Now, do need to tell you that two instances, one when it's closest to the Earth, two when it's farthest from the Earth, right? The velocities would be perpendicular to the distances from the Earth, distances from the Earth. The R1 would be perpendicular, this V1 would be perpendicular to R1 and this V would be perpendicular to R. At no other point other than these two extremities will this happen. Okay. It will happen also at the ends of the minor axis, but then for sure at the ends of the major axis of this ellipse, that is at the closest point and at the farthest point, the velocities would be perpendicular to the R, the corresponding R. Now, if m is the mass of the particle, do you realize that the total force that the particle experiences would be always directed towards the Earth? Therefore, this force will never produce any torque about the Earth, and therefore the total angular momentum about the Earth will remain preserved, right? Total angular momentum about the Earth for the particle enjoying this elliptic path will remain preserved. So the total angular momentum at this point, since V1 perpendicular to R1 is going to be m into V1 R1, and at this point it's going to be m into V into R. So m gets cancelled, so you have like a V1 R1 equals V into R, V1 R1 equals V into R. That's angular momentum preserved. Also, there are no dissipative forces, so the total mechanical energy will remain constant all the time. Total mechanical energy will remain. What's the total mechanical energy here? Half m V1 squared minus g mm divided by R1, right? Half m V1 squared minus g mm divided by R1. That's the total mechanical energy at P, the closest point, right? And that must be equal to the total mechanical energy here, half mv squared minus gmm by r, half mv squared minus gmm by r. Actually, r, when you solve for this r, it will actually have two values, because this condition would be true when r is the r corresponding to the closest point as well as r corresponding to the farthest point. So when you solve for r, this equation, one of the values of r that you're going to get would be r1, would be r1. Reason I tell you, you'll have a quadratic in r, because this v could be written as v1 squared r1 squared by r squared. So realize that I don't need to solve this equation blindly. Just to tell you what we need to do, half m. This v I can write as v1 squared r1 squared by v squared, by r squared, sorry. By r squared minus gmm by r plus gmm by r1 minus half m v1 squared equal to 0. This r would correspond to r closest and r farthest. Do you realize that it's a quadratic in r? In fact, it's a quadratic in 1 by r. You could look upon this as a quadratic in 1 by r, whose one of the roots would be 1 by r1, whose one of the roots is 1 by r1, the closest point, right? So then, So sum of the roots of this quadratic, the sum of the roots of this quadratic would be 1 by R1 plus 1 by R2. R1 for sure is one of the roots. R1 for sure is one of the roots, which is the closest point. R2 is what we are seeking. 1 by R1 plus 1 by R2 minus B by A minus B by A. So then that's like GMM by M. B1 squared, R1 squared. Yes or no? Where obviously this gets cancelled, and you can readily see that GM is V0 squared into R1 squared. This you can plug in. GM would be V0 squared into R1 squared. V1 squared is root 5 by 4 times V0. V1 is root 5 by 4 times V0. So 5 by 4 times V0 squared into R1 squared. How about it? GM V0 squared by R1. GM V0 squared by R1. So that makes it 8 by 5 R1. 8 by 5 R1. 1 by R1 plus 1 by R2 is 8 by 5 R1. So 1 by R2 is readily obtained. 1 by R1 into 3 by 5. R2 is 5 R1 by R2 is 5 R1 by. You know what all I did here? Right? GM is V0 squared into R1. So this would be R1 squared, So it will be 1 by R1 aega. V0 squared into R1, right? So cut jayega. So it will still be 1 by R1, 8 by 5 R1. It will be 8 by 5 R1, right? So let's look at 13. So just two principles involved here. One is angular momentum conservation. The other one is energy conservation. Can I wrap this up? 13. Right. So here we have a spherical shell. This is not a solid sphere, a spherical shell of mass m and radius r. And there is this particle that falls from the point P, descends to A, and it reaches the diametrically opposite point P. We want to be able to find the time it takes to go from A to P. But let's see what happens by the time it reaches A. By the time it reaches A, say it develops a velocity v. Now you can't say the loss of potential energy is mgr. The gain in kinetic energy is half mv squared, but the loss of potential energy is not mgr. Why? Because g is not constant over this distance r, which is comparable to this radius r. So you can't take g to be constant over this distance, right? So in any case, the loss of potential energy is potential here minus potential there. Potential at A is like minus g mm by r is the potential energy at A, right? Minus the potential energy at P is minus g mm by 2r. That's a loss of potential energy. That's the loss of potential energy. Yes or no? Potential energy at A minus potential energy at P. Or in fact, it should be potential energy at P minus potential energy at A. I'm sorry, I'll just fix this. Potential energy at P minus potential energy at A would be the loss of potential energy. Yes or no? So potential energy at P is minus GMM by 2R minus potential energy at A is minus GMM by R. That's the loss of potential energy. That's the loss of potential energy. And this must be equal to gain of kinetic energy half mv squared. Yes or no? So V can be found from these considerations. So velocity at the entry of this hole is known. Velocity at the entry of this hole is known at this point. Now when it enters this shell, the gravitational field inside the shell is 0. Right? You had for an electrostatic shell, the field inside the shell is going to be 0. So the gravitational field is going to be 0. That means no force is experienced by this mass because of the shell when it enters the shell. You know what I'm saying? So if no force acts, this journey AB is unaccelerated. That means this journey AB takes place at constant velocity. So the time taken from A to B is going to be AB divided by V is going to be the time taken, where V is known from energy considerations. The time required from A to B is 2R, which is AB, divided by the V that you can obtain from this equation. That's going to be the time it takes. I hope all of you realize why E is 0 inside the shell. No force is experienced by the mass when it enters the shell. V is constant, E is 0. Just draw analogies between gravitation and electrostat, you know. If you have a sound foundation in electrostats, then all of this would look exactly like that. An Earth satellite is revolving in a circular orbit of radius a and velocity v0. Velocity v0. A gun in the satellite is aimed towards the Earth. A gun, the satellite S, is aimed towards the Earth with a muzzle velocity equal to v0 by 2. The muzzle velocity equal to v0 by 2. Calculate the maximum and minimum distance of the bullet from the center of the Earth during the. Now, muzzle velocity means relative velocity relative to the barrel. Velocity relative to the barrel. That's what muzzle velocity. So then the total velocity of this particle is going to be the velocity of the gun, which is v0, plus the muzzle velocity. v0 plus the vector addition with v0 by 2 will give you the total velocity of the bullet. Will give you the total velocity of the bullet. That means the velocity of the bullet would be the resultant of the relative velocity plus v0. This is the velocity of the bullet, which is root v0 squared plus v0 squared by 4, which is root 5 by 4 times v0, greater than the orbital speed at that point. Greater than the orbital speed at that point, and therefore will pursue an electric trajectory. In this case, however, unlike the earlier case, this point F is not the point which is either closest or farthest from the Earth, because the velocity of the bullet in this case is not perpendicular to the R at this point. So this is not the point of closest or farthest approach with respect to the Earth, right? So like the previous case where the initial value of R was that R1, in this case the initial value of R is not A. The point closest to the Earth or farthest from the Earth is not A. Yes or no? But in any case, say whatever be the closest or the farthest point with respect to the Earth, say this was the Earth, and say this was the point closest or farthest from the Earth was R. At that point, be it closest or farthest, the velocity must have been perpendicular to R, irrespective of whether R is closest or farthest from the Earth, right? So then, you can conserve angular momentum like you did about the Earth, right? Realize that the velocity of the bullet has a component towards the Earth, which is V0 by 2, and has a perpendicular component, which is V0. This V0 by 2 will not contribute to the angular momentum about the Earth because its line of action passes through the position of the Earth, whereas this V0 would contribute angular momentum about the Earth as mv0 into A, right? And the angular momentum in this case is going to be mv into R. So we essentially have, cancelling m from both sides, v0 into A is v into R, where v are velocity and radius combinations at the closest or farthest point, right? Now, between S and this point P, you can also preserve the total energy of the system, total energy of the system. Now, at this point, what's the total kinetic energy of the particle? Half m into the square of Vb, that is 5 by 4 into V0 square. That's the kinetic energy, right? And the potential energy at this point is going to be minus gmm divided by A is the potential energy, minus gmm by A. M is the mass of the Earth. And at this point, what's the kinetic energy? Half mv square. What's the potential energy? Minus gmm by R. This V you can write as V0 squared A squared by R squared. You will get a quadratic in 1 by R, and you can solve for 1 by R. Two values of R, 1 by R would emerge. One would give you, the smaller one would give you the nearest point, the larger value of R will give you the farthest point. That's all that is. Where this V0 eventually in your final computation, this V0 you can plug in as root gm by A. This V0 you can plug in as root gm by R, the orbital speed. This V0 was originally the orbital speed, the circular orbital speed at a distance A. So this V0 was originally root gm by A. So you can plug in this V0 as, or wherever required. What you could do is, instead to eliminate gm, you say gm into g into capital M is V0 squared. That's what you do. So instead of changing this, change this, because this looks ugly in its presence. So, and then solve for R squared. Solve for R. So there is just a slight distinction between this and the previous case. The previous case was one in which you already had the closest point. In this case, this was neither the closest point nor the farthest point, right? A body is launched from the Earth's surface at an angle alpha equal to 30 degrees with respect to the horizontal. This is the horizontal. Find the height to which the body will rise. M is the mass of the Earth and R is its radius. Alright. Now, it will take up a certain trajectory. Obviously, it's greater than the orbital speed. V0 is greater than the orbital speed. So the path pursued is going to be elliptic. It's going to be elliptic about the Earth. So now, my claim is, if the maximum distance from the center of the Earth is h, if the maximum distance from the center of the Earth, is h, then at this point, the velocity would be perpendicular to the h. The velocity would be perpendicular to the h at the point P, where h is the maximum distance from the center of the Earth. If it was not perpendicular, this was h, and if it was not perpendicular, if the velocity was not perpendicular, then realize that there would be a component of the velocity which will cause h to increase. Yes or no? If it was not perpendicular, if it was inclined at an angle theta, then this v cos theta will cause h to increase, and this h wouldn't have been the maximum. So then for this h to be a maximum, the velocity at this point ought to be perpendicular to the h velocity. And again, we've done before, we can preserve the total angular momentum about the center of the Earth. The angular momentum about the center of the Earth, O in this case, well, V0 could be resolved as V0 cos alpha and V0 sin alpha. V0 sin alpha will pass through the center, will not contribute to angular momentum about O, whereas V0 cos alpha, mV0 cos alpha will produce this into R as the angular momentum about O, and that must be equal to the final angular momentum about O, which is going to be mv into h, that's angular momentum conservation, right, about the center of the Earth. And then energy, total energy, because there are no dissipative forces, the sum total of kinetic and potential must remain constant. At this point, what's the kinetic energy? Half m v0 squared, the kinetic energy. What's the potential energy? Minus g mm by r. At this point, what's the kinetic energy? Half mv squared minus gmm by h. All that you need to do is, using this equation, v into h is v0 cos 30 degrees into r. Replace v in terms of h. In this equation, replace v in terms of h, you will get a quadratic in 1 by h. Solve for 1 by h, you will get two values of 1 by h. One would be closest, the other one would be farther. Take the larger, the smaller value of 1 by h will give you the larger value of h, right? And that minus r will give you the distance from the surface of the Earth. That's all that you need. Got it? So now we have two stars separated by a distance 10a. Problem 6. There is a star of mass m, star of mass 16m, and their radii are a and 2a respectively. A body of mass m is fired from the surface of the largest star. Body of mass m fired from the surface of the largest star. What should be its minimum speed so that it reaches the surface of the smallest star? Okay. Close to the bigger star, the force of attraction from the bigger star would be predominant compared to the force from the smallest star, the attractive force. That means the close to this bigger star, the force in the leftward direction would be small compared to the force in the rightward direction. So the mass m would decelerate, and therefore you would always expect a prospect of this small mass m to not reach the other star. Yes or no? Now, when fired with a velocity v, this mass m comes closer and closer, but decelerates. And while it moves further and further away, the predominance of this grows compared to this. So no, there would be some point P along the line joining C1 and C2, where the force because of the larger star is the same as the force because of the smaller star. To the left of P, this force would be predominant. To the right of P, the force because of this would be predominant. So then, if you can just about fire it so that it just about reaches P, then this will take over and will cause the particle to reach the smaller surface of the smaller star. So the objective is to fire it with a velocity v so that it just about reaches this point. This is the threshold point. Slightly to the left of this threshold point, if the particle is able to reach, then this will take over, and the attractive force of this will be more than the attractive force of this, and the particle will be able to reach the smaller star. So then the redefined objective is find the velocity v so that it just about reaches P. Right? Just about reaches P means just about reaches P with zero velocity. So that let's say the velocity when it reaches P is just about zero. But then what's P? P is a point where the attractive forces because of the two stars is the same. Now, which means at P, which is say this is R1 and this is R2. From the centers of the two stars, the distances of P are R1 and R2. So then, because of this smaller star at P, Gm into small m by R1 square, that must be G times 16m into small m by R2 square. R2 then becomes equal to 4 times R1. R2 then becomes equal to 4 times R1, right? So R2 would be 4/5 C1 C2, 4/5 C1 C2, 4/5 the separation between them, and R1 would be 1/5 the separation between them because they are in the ratio 4:1. So R2 would be 4/5 of the whole thing, R1 would be 1/5 of the whole thing. So R2 is like 8a and R1 is 2a. Such is the location of P. And you want the particle to just about manage to reach reaches P with zero velocity. When you fire it with a velocity slightly more than P, it will reach P with a non-zero velocity and will be able to cross over. And once it crosses over, this will take over and it will be able to reach the surface of the smaller star. So then, between this point A and this point P, let me apply conservation of energy. At A, what's the kinetic energy? Half m v square. What's the potential energy at A? Minus G times small m into 16m divided by 2a. Right? Because of this, but because of this also there is potential energy. So because of this, it's going to be minus G times small m into capital M divided by, realize that this distance is, this is A and this is 6a. I'm sorry. This distance is 10a minus 2a, 8a. I'm so sorry. See, this is 10a minus 2a. So this distance is 8a from the center of this, mm by 8a, and that must be equal to the total energy at this point. At P, it's going to be, because of the smaller star, it's going to be minus G small m capital M divided by 2a, and because of this, it's going to be G times small m into 16m divided by 8. P G times m into small m by 2a. This distance is 2a. This distance is 2a. Distance from the center of this is 2a. Take care. R1 is R2 are distances from the centers of P. But is there confusion in this? What we say? Resolve them. So this would give you the value of P. This will give you the value of V for which it's able to reach P with a zero velocity. What you need is to fire this particle with a velocity slightly greater than V so that it crosses. And then the task is done. So the minimum V would be this. Right? Slightly more than this would do the job for you. Got it? Shall we proceed? Four particles, each of mass m, move along a circle of radius r from symmetry. This is how they are located. Let's say A, B, C and D. And they move under mutual forces of gravitation. Find the speed of each particle. Let's say the speed of each particle is v. Since they are identically disposed, you don't have to look at each particle. You need to look at just one particle. You need to look at just one particle. Very clearly. Look at the particle at A, for example. It experiences a force because of this F and F because of this. So then there are vertical components and let's say F1 because of this. Right? So the net centripetal force is going to be F1 plus F root 2 plus F root 2. Right? This is 45 degrees. F by root 2. This is 45 degrees. This is 45 degrees. So F cos 45 plus F cos 45 plus F1 is the required centripetal force mv squared by r. Right? So mv squared by r, the required centripetal force for the particle at A, is going to be force between these two, which is gm squared by 2r whole square by 2r whole square, that's F1 plus this F, realize, is gm squared by, this is r root 2, this is r root 2 whole square, and its vertical component is this into 1 by root 2 F cos 45 degrees, and then because of this you just double it. You can simply solve for. Alright, one problem I'll leave for your kind thinking. Do look at it in your own way. Once you're back.